Let's get the magnitude of the electric field vector at the center of any edge. Now the magnitude of that vector will be the same no matter which edge we take, so that works out by symmetry. Of course the E vector will vary depending on which edge we are looking at. The vector will vary because its direction will vary, but its magnitude won't vary. Its magnitude will be the same everywhere. So we're going to take this point here, which we will call C. So what are the coordinates of C? Well, it's midway between A and B, so we add the corresponding components in half. So we have 0 plus 1 is 1 divided by 2, 0 plus 0 is 0 divided by 2 is 0, and then we have 1 plus 1 is 2 divided by 2, which is 1. First of all, let's look at the E vector due to B, due to the charge at B. Well, it's going to be in this direction, away from B, and the E vector at C due to A is going to be in this direction here. So they're going to cancel each other out. So we can forget about the E vector due to the charges at A and B. Right, let's get the E vector due to charges at O and D. Well, we draw a line from O to C, and we just get our E vectors. The E vectors are on these two lines. They will have the same magnitude because the distance of C to both of these points is the same. Next we get the E vectors due to charges at P and S. So they look something like this. These two vectors will have the same magnitude because C is equidistant from P and S. Actually, the four vectors will have the same magnitude because point C is equidistant from the points O, D, P and S. Finally, let's consider the charges at T and R. So we can extend the line from R to C to get the E field due to the charge at R. As a matter of fact, the magnitude of this field will be less than the magnitude of these four blue vectors because charge R is further away from C than the charges S, P, O and D. Similarly for the charge at T. So these two purple vectors have the same magnitude, but their magnitudes is less than the magnitude of the four blue vectors. Now, as before, we need to calculate this quantity here. So we need the magnitude of vector Ri. So that's just the distance of the charges to the point C. So let's get this distance here. So we take the coordinates of C and subtract the coordinates of S. So it's a half minus 0 squared plus 0 minus 1 squared. Well, that's just the same as 1 squared, plus 1 minus 1 squared. So we have the square root of 1.25 for that distance. And these four distances here shown in black that I've highlighted in black are all square root of 1.25. Let's get the purple distances. So we have to take the coordinates of C and subtract the coordinates of this point here. So it's a half minus 1, that's minus a half squared, same as plus a half squared. 0 minus 1 squared, that's 1 squared. And then we have 1 minus 0 squared, that's 1 squared. So this gives us the square root of 2.25 meters. And of course these are the same. Now we also know that we need to get the vectors from the charges to the point C. So we have to get vector TC, vector RC, then DC, OC, SC and PC. So we have 6 vectors to consider. 4 of those vectors are vectors of equal magnitude. They're the vectors of length 1.25, and the other 2 vectors, that's the purple ones that we saw, have magnitude 2.25. Let's look at vector SC. So we take the coordinates of C, that's the head of the vector, and subtract the tail of the vector, which is 0, 1, 1. So the tail of the vector is at the charge, the head is at the point we're interested in, getting the field. So we have a half minus 0 is a half, 0 minus 1 is minus 1, and then we have 1 minus 1 is 0. Let's look at PC. We take the head of it, which is a half, 0, 1, and subtract P, which is 1, 1, 1. So we have a half minus 1 is minus a half, 0 minus 1 is minus 1, 1 minus 1 is 0. Similarly for OC, we have a half, 0, 1, and we need to subtract O. Well, that's just 0, 0, 0. So we just get C there. We just get the half, 0, 1. And finally for DC, we have a half minus 1 is minus a half, and then we have 0 minus 0 and 1 minus 0. So these four vectors need to be divided by the cube of their magnitudes. Well, their magnitudes are the square root of 1.25. We need to cube that, so we get 1.25 to the power of 3 halves. And we need to multiply by the charges. Well, the charges are all 1 nanocoulomb, or 10 to the minus 9 coulombs. So we need to sum those four vectors, or sub I. So that'll give us the field due to those four charges. Then we have to consider the field due to the two charges that are further away. So we need to get vector RC. Well, that's a half 0 1 minus 0 1 0. It's going to be a half 0 minus 1 is minus 1, and then we have 1 minus 0 is 1. Vector TC is a half minus 1 is minus a half. 0 minus 1 is minus 1, and 1 minus 0 is 1. So these are written as column vectors here. Okay, so these are the other two vectors. So R sub I refers to the 6 vectors. 4 of them have the same magnitude of root 1.25, and the 2 that we just looked at, the 2 purple ones, have magnitudes of root 2.25. So for these two, we divide by the cube of their magnitudes, which is root 2.25 cubed. Now the charge is the same for these two vectors, so that comes out of the whole lot, 10 to the minus 9. And of course the 4 pi epsilon 0 is the same for everything. So we just sum up the corresponding components and we get our vector. Notice that the x component of it is 0. That makes sense if you consider the symmetry of these 6 vectors. The x component is in this direction, and you know, the x components will all cancel out to 0. So here's the vector. We could write this using I, j and k, but we're not interested in the vector. We're only interested in its magnitude. So we square the components, sum them, take the square root, and we get 25.72.